All right. Ball Street Fighter 2 Blanca. I guess for Street Fighter, man, I have a favored couple, and it's gonna be like everyone in Street Fighter is my favored, but Dulcine has had such a effect throughout the years on me. Akuma, Ryu, Ken, sure. Blanca, Zangief, the Native American dude, T-Hawk. Wow, this is going to be a non-related tangent, but T-Hawk. Anyway, back to reality and the hard sciences. All right.
We're going to talk about navigating change in the context of emerging technologies underlying bioengineering. And along the way, we'll have this interesting topic, abiotic data storage. So let's get right into it. Pixar is a world-famous animation studio. They're such a success, they must have always been a success, right? Not so fast. How did Pixar navigate the change that was relevant to them when they were just beginning? What's really interesting is you can read about this story, and I'm just pulling two paragraphs from a very neat article published 10 years ago with one of the people who helped get Pixar going, Alvy Ray Smith. And so let's just read this bit of text to see what we can learn. When we moved to California, we got close to making a computer animated movie again in the mid-1980s, 1985. It's the second time they're trying to do something. It's going to be an interesting movie about a monkey with godlike powers. Something's missing from anyway. We had somebody who would pay for it, and we had a story, and the marketing looked good, and computers were still too slow. The projected production cost was too high, and the computation time way too long. What's he talking about? Well, they have a computer animated movie, and so they have the idea for what the movie should be, but actually making the movie itself is going to use computers to render the images. Remember, this is 1985, plus or minus, or thereabouts. And so the computers weren't powerful enough. It was the second time they had this experience. Apparently they tried this earlier and they couldn't do it, and they tried it again in the mid-1980s. And in the red, we had to back out of the deal. It was too expensive. Computers were too slow. This time, they write, knew enough to correctly apply Moore's law. We had to wait another 5 years to start making the first movie. And sure enough, 5 years later, Disney approached us to make Toy Story. So what's interesting here is Pixar didn't start out as a huge success. In fact, it looks like they tried to make a movie, they failed. And then they were about to try again. But they learned from their first failure, like, we better check how slow computers are, how fast computers are, how much they cost. And they're like, oh, we can't do it again. Almost made a second mistake, but at least now you have 2 data points, we can't do it. But anybody with 2 points knows that you can make a line. If you can make a line, then maybe you can extrapolate or project that line into the future. Right? So it's so interesting. And I really love this example because what you see today existing as the big successes, it didn't start that way. And oftentimes in the starting of things, you have to learn and fail and learn and then figure out what's possible and when things are possible. Well, this is for computing, and movies. What's this got to do with bioengineering? Let's use this as an example to dig a little deeper and extract the mechanisms by which we might figure out how to understand what's going on and extrapolate into the future and decide what type of bionaut or bioengineer we want to be. So to stick with the Pixar example, like, how much cheaper did using computers to render animations get between 1985 and 1990? Because that's where this little anecdote ends. And what information would we need to answer this question? But the most important thing is framing the question, because once you frame the question, you're like, how do I figure this out? You could just go ask anybody you know, like, what's happening with computers? Right? And once you start asking questions like that, you'll start to get answers like, well, what is happening with computers? In the case of computers, one of the most famous trends that's relevant and is cited in this example is shown here, so-called Moore's Law after one of the founders of Intel, Gordon Moore. And so this is a plot over time. It's a line, it looks like, starting around 1970 and going to 2011. So that 40-year period, that's the x-axis. And then the y-axis is transistor count. And it's basically how many transistors are on a computer chip. And the points on this line are different types of computers or computer cores or microprocessors. And if you look carefully at the y-axis, you see that it's a logarithmic y-axis. Like it's going up by a factor of 10, a factor of 10, a factor of 10. It's an exponential axis. So a straight line with a logarithmic y-axis means exponential growth. Computers are doubling in power about every 2 years, as measured by the number of transistors on a computer chip. This is what the Pixar founders were learning about when I say Moore's Law. And so, 1985, not fast enough, but if we wait 2.5 years, the computers might be twice as good after 2 years, twice as 4 times as good, almost 8 times as good, maybe 6 times as good. It's like almost 10 times as good, right, in 5 years. Like 3 doublings is 2 times 2 times 2 is 8 times more powerful. So every 3 to 4 years, your computer's getting 10 times more powerful. That's the slope of this. Now, they had learned from their 2 experiences that computers were following, the increase in computing power is following this trend. So like around this time, they thought we'd be able to afford making this computer animated movie.
Sergeant? Yes, sir. Establish your recon post downstairs.
So by the time we get to this in the theaters, right, it looks like a big success, but the big success is derived from decisions that were being made back in 1980, 1985. For Toy Story to arrive in theaters in 1995, the Pixar team had to be making smart decisions in the 1980s. Begs the question, what smart decisions should you, as, like, there's going to be a lot of bioengineers. They're just going to be following instructions. But who's going to be the bionaut? Who's going to be the bold bioengineering leader? And if you want to be in that second category, it's like, what smart decisions should you be making when, including today, about the right time for doing different types of bioengineering projects and possibilities? So that's what this is about. That's a warm-up. I like thinking about this through the perspective of surfing. If you've never seen surfing, here's what it looks like. This is next to San Francisco in California. When you see somebody surfing, the drama of surfing is what captures your attention. But for today's class, I really want you to think about where these wave and how they're changing over time. There's some engine somewhere far away, a storm, that's causing a trend, this swell. And then the wind and the topology of the ocean bottom and the tide are other physical factors that shape the wave. But the key thing is to understand that there's some engine somewhere, some trend that's creating this pulsing set of waves. It's like there's some trend that's creating changes in computing power. There's some trend that's going to be changing the capacities of bioengineering power, which we'll get to in a minute. And we've been talking about earlier this week already. But if you can see these trends, then you can, they're generating these pulses, these waves. You can understand where the wave's going to be. Then you can decide where you want to be with respect to where the wave's going to be, and then you can surf the trends, right? So it allows you, if you understand what's going on, to say, do I want to position myself there, and when do I want to position? Maybe you do, maybe you don't. The most important thing with surfing is not getting out there surfing per se. It's like understanding where the wave's going to be and then reading what's going on and then making a decision about where to position yourself. So that's the gist of it from just a totally different perspective. Turning this back to bioengineering, title of the slide, what are the emerging trends beyond computing that are or will likely impact the practice or impacts of bioengineering, if any? Well, here's something, right, that
something got skipped. Right?
That are or will likely impact the practice or impacts of bioengineering, if any.
If any.
Well, here's something, right, that helps us understand changes with respect to the tools we've been looking at this week. So we're going to talk about sequencing of DNA and synthesis of DNA and trends related to that. Of course, you want to understand how these tools work, but if you want to be a bionaut, you have to understand how these tools are turning into trends, meaning change in DNA sequencing and DNA writing capacities over time. So to get to that, we need to find clues. And the best way to find clues is just go look for clues. I know that sounds really trivial and maybe esoteric. I'm just going to give you some examples. And as we go through these examples, I'm going to pose some questions so that you can practice and gain confidence with, like, how do I find what the trends are? So here is a totally esoteric document from 1996, Cellular Computing, Summer Study. But at the top, you can see this symbol on the top right, DARPA. You should ask, what is DARPA? And you can find a Wikipedia article. I'd encourage you to read it. DARPA is a US federal agency whose mission is to create and prevent surprise, technical surprise. It was started by the United States Congress in response to the Soviet Union launching Sputnik. And that was so alarming, having another nation state surprise us with this object orbiting the Earth and sending out little radio signals. It's like, we don't want that to ever happen again. So how do we avoid that? We must create our own purpose, mission-driven organization to make sure we're never surprised by another country's technology. And the only way to do that is to make sure we have the most innovative technologies. That's one way of describing what DARPA is about. Maybe you could learn more. Maybe one or more of you will be DARPA program managers. And I bet and expect one or more of you might be the DARPA director in the future. Wouldn't that be interesting? Well, anyway, let's go back to this study. You can track down the study and download the whole thing for free from the MIT library. And there's this incredible plot. It's such a simple bar graph in the middle of this study. It says sequence genomes. It's got 3 bars on the graph, and then it's got 95, 96, 97. Those are the years 1995, 1996, and 1996. Number of microorganisms. So this is a representation of how many genomes have been sequenced for microorganisms on the entirety of the Earth in the history of human civilization. And the answer in the year 1995 is 0. And then in the year 1996, the answer is 2. And that's when they had their study. And I guess they must have been guessing about how many would be sequenced the next year. And it's like, there's going to be 10. Right? So it's like, okay, we have 0 genomes sequenced in 1990, even though Sanger sequencing, as we learned, was invented in the 70s, wasn't applied to bacterial genomes yet. It had only been applied to some virus genomes. So 0, and then it goes to 2, and then it goes to 10. And I love how they take 3 data points and make this unbelievable slide title. Biochemical knowledge is undergoing explosive growth. That's a bold statement. But you know what? They weren't wrong. They were right on target. And if you keep reading in this document, there's other things. It's like, the DNA has very dense molecular memory. You could store 100,000 bits per cell within this spatial feature. So one of the places you can find trends and learn about the future is to find the organizations whose mission is to understand trends and invent the future, DARPA being one of them. But look right here again. 25 years ago, people are learning about the trend in sequencing. It's undergoing explosive improvement in capacity. Now, we can quantify this in more detail. This is work done by Rob Carlson. What Rob is doing is time again on the x-axis. We're familiar with this from Moore's law. In fact, Moore's law is replotted on here on the blue line. And so we see transistors per chip on the y-axis. But we also see the red and yellow line. And these have different y-axes. These are the number of bases of DNA or nucleotides that a person could read or sequence in a day. All right, so that's the red line. How many nucleotides could one human being sequence in a day, given the technologies of that time? So in 1985, it's looking like it's somewhere between 10,000 and 100,000, 1 times 10 to the 4th, 1 times 10 to the 5th, right here. So call it 20,000 a day. But you fast forward to 2005, and it's gone up, and it's somewhere between 1 million and 10 million. And if we jump ahead, now it's somewhere between 10 billion and 100 billion. Well, so that's an exponential increase in DNA reading capacity. And it's trending actually and accelerating, if you will, faster than Moore's law. So in other words, DNA sequencing over your entire lifetime, more or less, has gotten more powerful, faster than computers have been getting better. And then the yellow trend is less mature, but it's writing DNA synthesis. So in 1990, a person maybe could synthesize 100 nucleotides in a day. And by 2005, you could synthesize 1 million nucleotides in a day, depending if you had access to the latest tools. Wow. So we saw what happened with computing. Just one example, computing getting better, and then suddenly we've got computer animated movies. But now, underneath bioengineering, if DNA is central to all of 21st century bioengineering and everything it can do, the two tools that are right upon DNA, touching DNA, DNA reading and DNA writing, they're moving out like gangbusters and following trends as profoundly, changing as computers were. Well, what's this going to mean? Let's use some examples. Surprise. And I don't really mean surprise, because if you can really start to get into these trends, none of this should be surprising. You're anticipating this as we're learning to surf along these trends of DNA read-write. About 10 years ago, 11 years ago, some colleagues wrote a book, and then they used DNA synthesis to encode their book in DNA. So they took an entire book, which is an analog object, but of course you can represent the book as a digital file that you might download to read on a tablet reader. But if you have as a digital file, zeros and ones, if you could map the zeros and ones to ACs, TGs, we'll talk about that later, then you could synthesize DNA, storing the information of zeros and ones. And so instead of having a physical copy of your book or a digital file on your tablet or laptop, you could have a test tube, and inside the test tube is synthesized DNA. It's not alive. And instead of it being an open reading frame for a protein or anything to do with biology, it's just data. So that was done for the first time over 10 years ago. And as soon as you start to think about data storage, like archival data storage, how big a market is that? It turns out way big. And so then you can ask the question, like, what if the people who want to store data have a much bigger demand for DNA synthesis than the people who want to do bioengineering? Because just more data to store than DNA to tinker with for solving a disease or something. Once you start to see something, you just keep seeing. It was like, I just saw that car, and now suddenly you see 10 other instances of the same model car. Like once you start, so people are putting information in the DNA, you just find more and more examples. So that video from the musical group OK Go, suddenly there's this example coming from Microsoft and the University of Washington up in Seattle, and they're taking a high definition music video from the band OK Go, and also the Universal Declaration of Human Rights in more than 100 languages, and the top 100 books from Project Gutenberg, and the Crop Trust Global Seed Database, and they're putting all of that data into synthesized DNA that can sit in a test tube somewhere. 200 megabytes of data just got pushed into DNA synthesis, and now you've got a test tube with microscopically small DNA molecules encoding the music video for the band, the Universal Declaration of Human Rights. What? Is it surprising? Well, once you're seeing the world in this way, it's like, oh no, I expect more of this might be happening. People are going to put more and more data in the DNA. And now you just keep looking. In the year 2017, the Library of Congress, the US Library of Congress, is holding a workshop. What do the librarians think about DNA data storage? Well, let's have a meeting about designing storage architectures for digital collections. This happened in the fall in Washington, D.C. at the Library of Congress. And we can track this down and see what the agenda is. And it's like, okay, Seagate Government Solutions. That sounds very good, but conventional. Tape manufacturer consolidation. That's what I think about. I think about tape reels and storing data on tape. But if we keep looking at the agenda for this meeting, the next day on September 19th, we see alternative media and the future. And there's all these speakers, and then alternative media in the future. And here we go, Karen Strauss, who was the researcher on the preceding slide from the University of Washington and Microsoft Research. Hwajun Park, DNA storage update. Whoa. So between the year 2012 and 2017, in 2012, the first book goes into DNA. You could say, oh, right time to do some bioengineering might be. Now, I want to switch gears for a moment. We'll come back and talk about surfing in a couple different ways. But I want to dig into why DNA might be the ultimate digital data storage format and how to put data into DNA. And the reason is subtle, but in my opinion, truly profound. Yes, DNA is tiny. So, you know, you've got a carbon ring, and then you could put 2 bases on the DNA. And so for 5 carbons, you could store 2 bits of data. We'll get to that. So it's super high density, like 1,000 times greater than most things. DNA, if you keep it in a dry place and, you know, don't change the temperature or irradiate it, it's pretty stable, right? So it lasts for hundreds of years, thousands of years. But the kicker is really the property on the right. When I talk to librarians, they had to teach me this. They're very skeptical about putting their most important information, the library, into digital archives because the technology of digital archives has been changing so quickly. You know, and if you're a librarian, you want to make sure your library's around in 100 years or 500 years, would you feel comfortable putting it into a compact disc or a DVD or, you know, a USB stick? Or like these technologies don't even last that long, but for them, they also have to think about the people visiting the library in 100 years. Like, are they going to know how to use a USB drive? Like, how many people know how to use an 8-track tape still? How many people, do you have an 8-track tape player where you are? Right? That was state of the art just a few decades ago. Now imagine like what's going to be the technology that's relevant for digital storage in 100 years. The cool thing about DNA from the librarian's perspective, and again, they had to teach me this, is people are in love with themselves. We're in love with ourselves. And we have DNA inside us, and we like reading out our DNA. And so if you can move your library into DNA, you can have confidence that if people are still around, if Homo sapiens still exists, that it's very likely there'll be DNA sequencers, there'll be readers for reading out the tape, right? And so that's the subtle but profound reason. Doesn't matter how immature it is right now. Wow, if you can get your library into DNA and make that technology better over time, you can guarantee that the readers will exist and people who know how to use the DNA readers will exist in 100 years, 500 years, 1,000, for as long as people exist, right? So it's the ultimate, you know, obsolescence insurance policy. It's just not, DNA is not going to go obsolete from the perspective of Homo sapiens. So puzzle with that in your mind until you understand it. Like that was something that was a really big aha for me. How to store DNA, data in DNA. Simplest way to think about it is if I'm going from bits, zeros and ones, then I could just say, well, you know, a 0 is going to be represented by an A or T, right? And if I see an A or T, or if I put an A or T on a DNA strand, that's a 0. If I have a 1, I want to put it on DNA, a C or a G, right? So that's a simple 1 to 2 transcoding. It's not the most data dense. You could obviously store 2 bits of data in each position on DNA because there's 4 options, right? So you could store a 0, 0 into an A, and a 0, 1 into a T, and a 1, 0 into a C, and a 1, 1 into a G, and so on. So these are pretty straightforward, simple transcodings. There are other things you can do, which instead of using binary digits into DNA, you could say, well, we want to make sure that when we get to the sequence of DNA encoding the data, that the base that's being used is always changing, right? And so we're going to use a ternary digit code where the base that follows depends on the preceding base. And you can see if you can work through how to do that. But there's an infinite number of ways to go from information into DNA. One thing I should say very plainly is you don't have to go through binary digits or bits, right? Let's say you wanted to encode music into DNA, like a piece of piano music. You could just say, well, here is the sheet music and the notes on the sheet music and the octaves, and I'm just going to directly give different notes in the sheet music different sequences or letters of DNA. So I just want to take care, you don't have to do DNA data storage by going through binary, right? Infinite options, right? And part of the puzzle you've got in front of you is to consider imagining one or more of these. One thing I want to highlight, which is subtle, is, you know, like, why not just go with full data density of 2 bits to 1 position? And the answer comes down to reliability of reading and writing. And as we've heard, these tools for reading and writing of DNA are amazing, but they're not always perfect. And we can make things easier for the tools if we, for example, are always making sure that the letter is changing A, C, T, G from one to the next. Why might that be the case? Well, when you do the actual reading out off of one of these machines, you might get a peak that says, oh, the base right here is an A. And if you have a lot of A's in a row, the machines is going to say like, ah, and you're going to have to be parsing that signal really carefully, if it's possible at all, to discriminate between, was that 2 A's or 3 A's? Was that 5 A's or 6 A's? But if instead you're trying to read out a sequence that's A, C, T, G, C, T, where each position is always different, you'll get a very discretely different signal, and so it makes the reading more accurate. So we can choose data storage codes that make it easier to do read and write. Whether you should do that or not is going to depend on other variables in a particular application. And just to close on this, if you want to learn more and if you want to see more evidence for what's going on, suddenly there's the DNA Storage Alliance, the DNA Data Storage Alliance with this website. And look at all these organizations that are now clustering around this topic to try and figure out how to invent this version of bioengineering future. Were you expecting in bioengineering suddenly it's about libraries and librarians and archival data storage? Like, I wasn't, at least not until I started thinking about this DNA read-write trend and how it might impact things, beyond living systems directly. What else? What else might we expect seeing these trends? What else could be happening? I'll give you some other examples. When DNA sequencing got cheap enough, it turned out that it changed how healthcare could be provided for pregnant women. For example, our youngest child is 6 years old. And when Christina, my wife, was pregnant with our second child, we had a new experience at the hospital. They took a blood draw, and in the blood of healthy pregnant women, there is DNA circulating from the fetus. And that's normal. And you can use DNA sequencing to read out that DNA and determine what's going on with the fetus genetically. So 10 weeks into our second pregnancy, we knew that our second child would be a boy because Christina, my wife, had Y chromosome DNA from the fetus, male chromosome DNA, in her blood. This is before you can see what's going on with ultrasound or another method. With our first child, this technology didn't exist in the hospital here. Oh, there's 2 data points. What's going on? This is called cell-free DNA or non-invasive prenatal screening. It's a technology that can displace amniocentesis or more invasive ways of collecting samples from a fetus. Whoa. Here's something at the opposite end of the spectrum. Maybe you live in a neighborhood and you're worried about dogs pooping everywhere. What if you could register your dog and its DNA and have some, by the way, I don't know if this is a good idea or not, it's called poop prints. Like, what if you could use DNA sequencing to determine who wasn't cleaning up after their dog, right? Well, that's something that becomes possible apparently when DNA sequencing becomes accessible and affordable enough. Here's another example. It's like, okay, somebody used a 3D printer to print a bunny rabbit, but they didn't use just a normal 3D print material. They actually, in the material that they were using to do the 3D printing, the polymers, they included glass beads, and inside the glass beads were synthetic DNA, and the synthetic DNA was encoding the data for the computer file to 3D print the rabbit. Stated differently, this abiotic plastic object has a DNA genome, which is the computer instructions for 3D printing this object. And so because of that, you could cut off a little bit of the rabbit's ear, recover the DNA, sequence it, get the computer file, and use that to print more rabbits, right? And so they're showing in the bottom this life cycle of an abiotic object that has its own instructions for reproducing itself encoded in DNA. DNA, it's not in a living system, it's in a glass bead, and just like, make more rabbits, right? They call this a DNA of things storage architecture to create materials with embedded memory. They put movie recordings in DNA encoded in the lenses of glasses. You could put all the information needed to rebuild civilization into DNA, and then put that DNA in glass beads and embed that in your refrigerator handle, such that if there is ever an apocalypse, you'd like, okay, we're going to reboot civilization by recovering the information from our refrigerator. You put arbitrary information in arbitrary objects. Is this surprising? Well, like, first time you hear it, but not if you orient within this context of DNA read-write are getting better and better. Here's another example, Annika Bio. They're using synthetic DNA to basically do provenance tracking. Like, where'd this thing come from? How's my food supply chain doing? If I have a whole bunch of lettuce and some of the lettuce has a pathogen that's causing people to get sick, do I have to recall all of it? What if I could spray different sequences at different points of collection such that I have finer granularity around the sourcing? And so what changes might bioengineers realize via DNA? We've seen now that there are trends, meaning changes over time with respect to DNA read and write capacity. And given these trends, maybe you should start tracking them. Maybe you could have like a little plot next to your desk at home or above your bed. Like, what's the DNA trend, right? So that over your life, my prediction would be over your entire life, there are going to be ongoing changes and improvements to DNA read-write tools. And I view DNA as the polymer of the century from a technology and economic perspective. So if you're tracking these trends, then you can be not just a bioengineer, but a bionaut, and position yourself to decide, just like Albie Ray Smith, like, when was the right time to do Pixar? I don't know what the Pixars are going to be for bioengineering yet, but I know somebody's going to figure them out, and maybe it's going to be you. And if you can follow these trends, it can help you decide what to do and when you want and what change you might want to make. Now, I want to end with a little snippet of, we've been talking about quantitative change, like, okay, it's getting a little bit cheaper, a little bit more powerful over time. But sometimes there's qualitative change. It's much harder to think about qualitative change. And the qualitative change I want to focus your attention on is what happens when you combine DNA sequencing and DNA synthesis. DNA sequencing lets me take an organism or a piece of DNA at some point in its history and turn it into digital information, the letters ATCG that I can act on through computers and computer networks. Synthesis, so sequencing lets me go from atoms to bits. Synthesis lets me go from bits to atoms. I can take that information, I can reinstantiate the genetic material, whether that goes into a living system or a library. Now, when you put sequencing and synthesis together, the language is going to sound funny, but it's the simplest way of saying it. We're making genetic material and genetic information interconvertible or fungible. You can go from bits to atoms and atoms to bits and back and forth and back and forth. And that's just shockingly new. Prior to these two tools coming together, all of life on Earth exists like you see in this little sketch I made at the top. From one generation to the next, you came from your parents, I came from my parents. If you have kids, they'll come from you, right? And that's normal, that's natural. But suddenly, we're through DNA read-write, we're creating a potential break in that lineage, that chain. And it's a very profound underlying qualitative change that's opening up. I'll give you 2 more slides just to help you think about what I mean by qualitative change. I'll use an example of music first, and then we'll go back to bioengineering. So it used to be the only way to hear music was to have an instrument and to play it. Like this gentleman is playing his interesting instrument here. Later on, we learned how to record music, and the movie here is showing a microscopic close-up of a vinyl record and how you can store stereo signals in a V-shaped trough. You can see the needle going back and forth in the left and right channels. Later on, we figured out how to turn analog storage into digital storage, things like compact discs, and that's what's shown in the bottom right. And then suddenly, this thing called Napster happened, which let you take the digital files and move them around via the internet so that you no longer needed to have the physical media. right? Now Napster becomes other things like Spotify or Tidal or whatever's popular today. But it's in this fourth quadrant, this top right quadrant, where the qualitative change gets to be revealed. That suddenly music is available anywhere in real time streaming through the internet, right? It's like, huh. So let's end with this. Here we see a person relating to perfume. What is perfume? Perfume, where do we get perfume? It's, plants and other chemicals are collected and mixed together in a perfume factory, and the perfume is placed in a bottle, and then somebody buys the bottle and then dabs the perfume over themselves, depending on how they want to smell and when. And that's what perfume's all about. How does qualitative bioengineering change related to DNA read write? How might that impact perfume? Just as one tiny example. Well, what if there was a website called iFumes? And on the website, you could download DNA code for 99 cents a pop. And the DNA code was for the biosynthetic pathways making different molecules that smell in different ways, odorants. And you'd go to iFumes, you'd pay, you'd download the DNA code, you'd build that DNA, and then you'd slather that DNA on your skin, transfecting the microbes on your skin, your epidermal ecosystems, so that now they'd be reprogrammed to make living perfumes. That's an example. It's a fantastical example for today of what it might mean to navigate qualitative change associated with bioengineering. So hopefully there's a lot more for you to think about, and maybe start with like, what did he just say? Did he really mean it? By the way, I really meant it. So let's wrap up. Do you feel like you're happening to the future, or is the future happening to you? When was the last time someone or something just futured all over you without asking your permission? Who was it? Was it Elon Musk? Did Elon Musk just future all over me today? Right? But how do you feel about this? Second, how can you develop and use understanding of trends, technical trends or otherwise, to give yourself the option of happening in the future, positioning yourself, as the waves are breaking? Where do you want to be? How good do you think bioengineers can get at reading and writing DNA? What do you think the DNA read-write tech of 2030, 2040, 2050, over your lifetime, what do you think it's going to look like? And like, as important, what's it going to feel like if you were using it? You can store information in DNA by converting bits and then to DNA. But as I mentioned in passing, you could just encode whatever information you want through some special codec, directly in DNA without going through bits first. Might be music, might be a drawing. Have fun with thinking about that and trying that out. Why might you skip the bits and just go right to the basics? Regardless, thinking back to the why DNA slide, remind yourself, like, why is DNA so ripe as a substrate for data storage if you're a librarian? Okay, that's it.
All right. Man, I love this True Andy guy, Professor Andy, through these lectures. Oh my gosh. And then one of these first couple lectures is talking about dreams and bioengineering, and kind of see how I named my playlist here, My Dreams. And let's see how Eternal Youth. See how the Google results are now. Spaceships for Everyone. And Resurrection. I don't think much changing